Hey, and welcome to another data structure video. And today we're going to be going over binary search trees. We're going over the basic operations that you really need to know: searching, inserting, and deleting. This is one that I would really recommend that you try to understand because this is an important data structure, and that you'll definitely use it a good bit, as it can be the basis for a lot of other tree structures that I'm going to be going over in the future. Okay, so let's get started. So what is a binary search tree? Well, there's a few properties that you just need to know, and they're pretty simple. The first one is a node can have at most two children. So it can have 0, 1, or 2. All keys or nodes in the left subtree are less than its parent node. All keys in the right subtree are greater than the parent node. Okay? Go ahead and go to an example so that understand it. All right, so here is an example of a BST. So we have the laser pointer. We have root node 55. Okay, so all nodes to its left are less than 55. So 25, 22, 39, 37. These are all less than 55. And we only have one to the right, 58, and it's greater than it. Okay. Now, if we can take another subtree, let's take 25. Well, all nodes to its left are less than it. In this case, we only have one, is 22. Then all nodes to its right are greater than it. So in this case, we have 39 and 37. Okay, that's how binary search trees work. Now there's a term just kind of get in your head and remember. It's called balance trees. Binary search trees don't care about balancing at all. All right. So we're going to go ahead and get into the next slide, which is going to go over searching. Okay. So here's an example, BST, the same one, and we're going to search for something. So let's say we want to search for the node 37. Okay. So what are we going to do? Well, you start at the root node. Okay. Always start at the root node. Is 37 less than or greater than 55? Well, it's less than, so we go to its left child. Is 37 less than or greater than 25? Well, it's greater than, so we go to its right child. And is 37 less than or greater than 39? Well, it's less than, so we go to the left child. And we found 37, okay? At each comparison, so when we say a comparison meaning is 37 less than or greater than something, whenever, like we did 55, we go to its left child at 25, you're always checking to see if that node is equal to the value you're searching for, okay? Whenever you end up coding it. So in this case, we did 3 comparisons and we found it. And there's a total of 6 nodes. So we found the node we're looking for um, with about half the comparisons of the nodes that are total in the tree. Why is that? Well, let's take a look. We have levels. Take these levels of the binary search tree. Okay, so basically this means the 0 level, the first level, second level, and third level. These are like rows in the trees. Okay, kind of went over this in the general trees video. It's kind of like how you calculate the height and the depth of a tree. So there's a mathematical operation where if you say 2 to the level you're at, so let's say we say 2 to the 0, that's 1. Don't ask me how to explain, that's just how it is, okay? And then the next one is 2 to the 1, that's 2. Meaning that you can have at most 2 nodes in this level, okay? The next one is 2 squared, and that's 4. So you can have at most 4 nodes in level 2. And then we say 2 cubed, because we're at the third level, and this is 8. So you can have at most 8 nodes in that level, okay? So what this is basically just saying is that searching for something in a binary search tree is really efficient. Doesn't, like, how you can have a lot of nodes. Like here, we can have all these nodes filled up. So at 1, 3, 7, and then 8, so 15 nodes here, and it only took 3 comparisons to find 37. Okay, so it's like really efficient at searching for something. So let's go ahead and move on to inserting. All right, so let's say we want to insert 45. Okay, well, basically we're kind of doing like what we just did. All right, so is 45 less than or greater than 55? Well, it's less than, so we go to the left child. Is it greater than or equal to 25? Well, it's greater than, to go to the right child. Is 45 greater than or equal to 39? Well, it's greater than, but there is no node there, so that's where we insert it, okay? We just insert it where we kind of keep going down the tree until it's greater than or less than something, and there's no node there. Boom, put it right there, okay? And that's pretty much all insertion is. Insertion's a pretty simple operation. It's just comparing, keep on comparing down the tree until one of the children node is equal to null. Put it there, okay? All right, deletion. Now this is a little trickier because there's 3 cases to deletion. There's a case for 0 children, 1 child, and 2 children. Let me explain. So let's say we want to delete the we want to delete a node that has a value of 37 in this tree. Okay, let's just kind of pretend we don't know what's there. So what do? Well, we have to try and find it first, right? Make sure it exists. So if 37 is less than 55, it's greater than 25, and it's less than 39. Okay, well, we found it. It exists. So now we want to remove it from the tree. Okay, this is the easiest case of the 3. So all you would say is you take node 39 and say node 39, its left child equals null. Done. It doesn't exist anymore in the tree. Okay, and that's pretty much it. If it was the right child, like say if 37 was over here and 37 still didn't have any node children or didn't have any children, you would just say 39's right child is equal to null, and that's it. Okay, so again, 37, the node we want to delete, has no children. So you go to its parent and set that its left child to null, and that's it, or its right child, depending on where it's at. That's all. Okay. So now let's set the case where a node we want to delete has 1 child. So in this case, we want to delete 39. So as we can see, first off, let's make sure it exists. Go down here. 39 is greater than 25. Okay, we found it. Now we want to delete it. So, but the problem is we can't just say 25's right child equals null because there's still a node there of 37. It still exists, and we have to do something with it. So we have to rearrange the tree just a little bit, okay? So what do we do here? Well, we want to get rid of 39. We know that for sure. So what do we replace it with? Well, whenever a node only has 1 child, whether it's the left or the right, so the node we want to delete, 39, has 1 child. It's, in this case, it has a left child. Well, you just basically replace that with 37. So we're going to say node 25, we're going to say its right child is now equal to 37 instead of 39. Just like that, okay? Then if there were any nodes attached to 37, they go along with it, okay? Because all we're doing is the reference point from 25 to 37. And 37 still has all the other references to these nodes, okay? And that's it. Okay, so now we're on deletion for 2 children. Now this is a little bit trickier. So let's just say we want to delete the node which has value of 25. Okay. Well, first off, we need to find it. So we start at the root, search for it. Right there it is. Okay, so we found it. We know it exists. All right. So this node has 2 children, 22 and 39. So how do we do this? We can't just get rid of it because we have 4 other nodes. If we just delete 25, well, we have 4 other nodes that are a part of the tree. So what do we do? Well, there's got to be a rearranging. And what you're going to find is, if you look this up, it'll say something like find the in-order successor or something like that. So all that means is that we need to find the next value in order of all of the values in the tree. So this is 25. Okay. The next value is 37. Right. So that's what we want to replace. So the node of 37 is what we want to replace with 25. Okay. So what do we do? Well, we what you need to do is you go to the right subtree because all the values to the right of 25 are going to be greater than it. All the ones to the left are going to be smaller. Okay, so you go to the right and then you go as left as you can. So you want to find the leftmost node in the right subtree. Okay. Now there is a case where um, if you go to the right and 39 is the only node, then it's just 39. Okay. If you kind of like in the code, you'll check to see if you keep going left, but you want to find the leftmost node in the right subtree. Okay. And then what you do is, let me change this color. You're gonna swap these. Okay, you're gonna swap them, and then once 25 is down here, you want to get rid of it. All right. So once you swap these, and then 25 is where 37 is, delete it, and then you will be good because this will be 37 won't have any children nodes because it's going to be the leftmost node. Okay. Well, actually, no, I take that back. It has a chance that it could have a uh, a right child, in which case you would move that up. So, like, if you went to the leftmost and say 37 had one child, well, then 39's left child will then be linked to um, the successor's right child. Okay, so that's pretty much it. Now we're going to be dealing with recursion, a lot of recursion whenever we do this. Okay, and if that concept is kind of new to you or you don't quite understand it, I will certainly love to make another video in the future about recursion because it's not magic. There's a reason it works, and I think that you can definitely understand it. Okay, I'll try to go over recursion on the next video whenever we code this. But if you don't quite understand it, it's okay. Um, but this will be a good introduction because BSTs use recursion a lot. You can do it what's called iteratively, basically using a bunch of if-else statements, but recursion uh, decreases the amount of code, and once you kind of understand it, it's a better way. Okay, so I hope you learned something. If you have any questions or comments, please leave them down in the comments section, and I will definitely try to help you out. Okay. All right. I'll see you guys next video. Thanks for watching.